Try to edit out any weirdness in the video, so if you have to blurt out something, I'll make a little notation on the board and I'll delete it. Because I know you can't withstand
It's already
yourself.
bothering me. Really
Is it?
bad.
Oh. And I wasn't even recording. That's funny. Like for instance, I'm going to delete out everything I just said. Okay, so let's start with 1, 1. Yeah, I gotta get rid of that. Usually I like squeaky markers, but not this time around. Alright, so exponential functions are basically this. Function, base, raised to some power. Base raised to some power. So there's a few things we have to be curious about. What can B equal? Are there things that B should not be? I shouldn't have used the letter B. What should B not be? To be or not to be? So let's look at a couple cases. Case 1. What happens if B is equal to 1? What's 1 to the x equal?
It's always going to equal 1.
It's always going to equal 1. That's not an exponential function. That's a constant function. And it's kind of boring in its sense. Along with case 1, we could also look at the other nonsensical one. What if B is equal to 0? What do you get? Well, 0 to the x is always 0. So that one is also not an exponential function. It's a constant function. So B equal 1 we have to throw away. B equals 0 we have to throw away. What about between 1 and 0? Let's write it this way. Is that legal? Oh, by the way, that's case 2, not 1. Dear Lord. So can B be between 1 and 0? So let's pick a number. What's the easiest number to work with between 1 and 0? And I'm going to write it as a half. Does that cause any problems? So what's going to happen is we're going to let x equal a bunch of numbers like 1, 2, -1, -2. It could be any real number, actually. We'll talk about that later. But a half raised to a power is kind of weird. Let's say, look at f of 2. So this would be a half raised to the second power. Well, what's a half raised to the second power? A fourth, right? Well, this seems unnecessarily messy. You know, if you're just taking a half and raising it to the second power, the only thing that's really getting squared is the number on the bottom, not on the top. So is there another way of writing a half so you don't even have to look at the 1? This goes back to those old stuff. I could leave the 2 in the bottom and it'd be perfectly fine, but it's kind of just messy. So can I take the 2 and yank it to the top? And if I yank it to the top, what has to change? What becomes negative?
The 2?
Something's going to be negative.
What you raising it to?
The exponent has to change to its opposite. So when you drag things through a fraction, the exponent's going to become its opposite. So another way of writing this, f of 2, would, well, what I really should say here is f of x, but that's okay. This would be 2 raised to the -1 raised to the second. And obviously that's still 1/4. And even better than that would be 2 raised to the -2. You know, power to a power multiply. So another way of writing this function at the very, very beginning, let's do it green, would be to write it as 2 to the -x. And I highly suggest if you see a fraction with a 1 on the top, write it as a negative exponent rather than as 1/2 to the x. This is nice, but we're out of elementary school. We can understand things that are a little bit higher nature. So I'd rather you write it this way. Now x can be any real number. And 2 is a nice little base, and you can raise 2 to any power that you want. So this is a perfectly fine function. So numbers between 0 and 1 are nice, but it's best to write it with a negative exponent. Numbers between 0 and 1. All right, what if we go the other direction? Bigger than 1. Do you think that's going to cause any problems? Case 3. What if we chose b to be larger than 1? Will that cause problems? Yeah. If I have f of x is equal to 10 to the x, that's bigger than 1. Can you raise 10 to any power? 10 to the first, 10 to the second, 10 to the third? Obviously those are going to work because that's how our real numbers work. What about 10 to the negative 1, 10 to the negative 2, 10 to the negative 3? Will that work? What's 10 to the negative 2 equal?
1 over 100.
1 over 100. When you write a number like 4.387, this is 4 times 10 to the 0. This is 3 times 10 to the negative 1. This is 8 times 10 to the negative 2. 7 times 10 to the negative 3. 10 to the is our place value system. So case 3 is perfectly fine. As long as the base is bigger than 1, we get an exponential function. The one I worry about is this one. And this is really hard to describe. What if b is that? What did I just say b was? Yeah, but that doesn't tell me anything. It just says less than 0. What is b really? Negative number. So when you see things like less than 0, don't read them as less than 0. Read it as negative. If you see greater than 0, read it as positive. It makes life a little bit easier. Is she mouthing off back there again?
I don't understand what that thing does.
What thing?
The little A Spanish thing on the bottom.
This?
No.
No, your rat thing, your rat
On the
bottom.
board.
Ah.
Is that
This
what-
works on sound waves. This is aluminum, so the sound waves bounce cleanly off of it. So I'll be writing up here, and the computer thinks I'm writing down here
Okay.
because it bounces, so I dampen it. It's called a dampener. Yeah, this thing's cool. It measures how far away from that device I am, and it measures the angle at which I'm writing,
Okay.
which is kind of neat. Ooh, I think I went beyond my boundary. Yeah, kind of. B is less than 0. The boundary's right there. So if I have b is less than 0, that would be like f of x is equal to negative 2 raised to the x. Now this one causes problems, but I have to show you why it causes problems before you actually believe me. I hate saying don't do this because I said so. Like don't divide by 0. You all know why you can't divide by 0, right? Why? You shook your head, now you get to answer. No. I could never get her to talk. I guess I'll show you later. There's reasoning. If I choose values for x, that's going to generate values for y. So we can do a little table here. So let's let x equal 0. If x is equal to 0, what's negative 2 to the 0 equal to?
0.
I forgot to go over one of the old stuff. Anything raised to the 0 power is equal to?
1. That's
1.
right.
So this will be 1. If I put a 1 here, that's negative 2 to the first power. What's negative 2 to the first power? Negative 2. If I put x is equal to 2, that would be negative 2 squared.
4.
Positive 4. If I put a 3 there, that would be negative 2 cubed. Negative 8. If I go to 4, it would be negative 2 to the fourth power, which is 16. Now one problem is this. The answers are going positive, negative, positive, negative, positive, negative as we go through the evens and the odds. For every odd it'll be negative, for every even it'll be positive. That's part of the problem, but that doesn't force it not to be what we would consider a function. All right, let's look at different types of values. What if I choose x equals a half? That's a real number. What's wrong with a half? What's negative 2 to the half power really mean? Talked about this earlier really quickly. It's a square root. A half power is the same thing as a square root. What's the square root of negative 2?
It's going to be imaginary.
It's going to be an imaginary number, so it's not real. So we can't even plot that. So all of a sudden we have this graph trying to go someplace. You know, graphs are usually connected dots and all that fun stuff. And at 1/2, there's no dot. So it's a broken graph. It's not what we consider what's called continuous. We'd rather do continuous functions. That's still not too bad. Then we can do things like 3/5. Now I'm not going to tell you what the answer is, but basically it's the 5th root of the number raised to the 3rd power, and the number was negative to begin with, so guess what the answer is going to be? Negative. So the answer would be negative here. If I do 4/5, the answer is going to be positive, because the 5th root would make it negative, but 4 negatives make a positive. So in this case where we're just between 0 and 1 here, we haven't even gone outside of it. If your fractional exponent is even in the bottom, it's always going to be not real, leaving a hole in the graph. If the number on the top is odd, your answer is going to be negative. If the answer on the top is even, your answer is going to be positive, as long as the bottom is odd. So this graph is positive, negative alternately, and it has holes for every even fractional exponent, denominator fractional exponent. So is this graph even nice?
No.
It's going up, down, and it has holes everywhere. So you can't even connect a nice, smooth curve from it. So this case here is not in other words, you cannot have a negative exponent for an exponential base. So you can't have 1, you can't have 0, and you can't have negative numbers. Everything else is perfectly fine. Numbers between 0 and 1, fractions if you want to think of it that way, or numbers bigger than 1. Generally, we want to keep our bases bigger than 1. Thus, if you have a half, you want to change it to 2 to the negative. If you have a third, you want to change it to 3 to the negative. It's just easier to work with numbers bigger than 1. Does that make sense so far? What constitutes an exponential function? Let's graph one. Sometimes graphing helps a little bit. The easiest base to work with, of course, is 2. So a lot of my examples will be using that. So graph f of x is equal to 2 to the x. This is one of the nicer ones to graph. It's also known as the doubling function. Like if you have $2 today and you need, tomorrow you'll have $4, the next day you would have $8, and then 16 and 32. Those numbers should kind of come in handy for certain things like, well, computers. We'll talk about that in a second. So if we're going to graph this, we'll just plot some points. Of course, you can always type it into a graphing program. It'll graph it for you, but it doesn't tell you why it looks like that. I highly suggest you start with negatives first, and then work your way into the positives. And try to keep them in order. Makes life a little bit easier to see the flow of the function. All right, so the first one would be 2 to the negative 3 power. What's 2 to the negative 3 power equal to?
Negative 1/2 to the 3rd power.
Which is?
1 over 8.
1 over 8. Remember we talked about that earlier? 1 over 8. What's 2 to the negative 2 power then?
4.
A quarter. 2 to the negative 1? A half. 2 to the 0? 1. Anything raised to the 0 is 1. 2 to the first, of course, is 2. 2 to the second is 4. 2 to the third is 8. See a little symmetry going on. When it has negative exponents, the number goes in the bottom. And it has positive exponents, it stays in the top. We can plot this. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I don't do precise graphing, but if you want graph paper, you can have some. Do you want it? I usually don't like it, but I have some. I think I have some. I got this crappy graph paper if you want it. Anybody else? Crappy graph paper. Somebody left it in my room one time, but I have better stuff. I think that'll work. I think for math classes, if you get the notebook that is pure graph paper, it is the best, because then you can just throw a graph anywhere in. But it's hard to find that stuff. I thought I had some other graph paper. Nope. All right, so let's plot some points. Let's start with the easy ones. 3, 8. That's over here. 2, where am I? 2, 4, which would be here. 1, 2, which is here. 0, 1, which is there. Then the fun begins. -1, 1/2. So it's right about there. Halfway up between 0 and 1. -2, 1/4, a little bit lower. -3 and 1/8, a little, half the distance to the x-axis. That's the best way to describe it. Half the distance to the x-axis. So the easy part of this graph is the right-hand side. We can kind of, oh, by the way, these are distinct points. It takes a lot of theory to say I can connect the dots. A lot of that theory says that this 2 to the whatever works for all real numbers. I can prove it up to rational numbers for you. The calculator would have to show you that irrational also works, like 2 to the square root of 2, which is really weird. But it's hard to prove that 2 to the square root of 2 is actually realistic. Once you get that idea down, then you can start connecting the dots. And you get a graph that looks like that. And that half of the graph is usually called exponential growth, because it's growing, but it's not growing as a straight line, it's growing exponentially. If we kind of made right to left our natural motion, the left-hand side is called exponential decay. But usually you just take the graph and flip it around and it becomes exponential decay. We'll talk about that in a second. So do these dots ever touch that x-axis? Why? Because that's 0. And you can never have a power that would cause 0 to come about. I mean, if you have 2 to the x is equal to 0, there is no power that you can raise this to get it exactly equal to 0. Can you get it close? You can get it really close. Half of a half of a half of a half of a half. It gets really tiny. So as this comes down, it'll never ever touch this x-axis. Do you remember the name for lines that are never touched?
Asymptote?
Asymptote. So this is literally a horizontal, let's see if I get this right, horizontal asymptote. One of the weirdest words in the English language. Asymptote. Asymptote, depending on how you pronounce it. So one of the key configurations of this graph is if I asked you to graph it, one of the things you want to find is where is the horizontal asymptote, depending on how you want to say it. The other key thing is this point right here, the y-intercept. It's usually 1 above the asymptote, depending on how you want to say it. I'm going to keep saying that, aren't I? So one of the key factors is finding that point that is 1 unit above the asymptote. Now that obviously can be moved anywhere in the picture, up, down, left, right, all over the place. You can even flip it, like if I put a negative in front of it and make it -2 raised to the x, it would take this whole graph and flip it down, then your point of interest would be 0, -1. So it's always 1 unit away from that vertical or horizontal asymptote. Not bad, right? For instance then, erase that mark. What if I was going to graph this? Remember transformations in functions? Like if you have f of x -3 plus 1 for some function that has a nice graph, what does the plus 1 do? Makes it go up 1, so this would be up 1. What's the -3 on the inside do?
Makes it go to the right 3.
This would be right 3. So the same thing's going to happen here. This piece right here is the inside of the function, the raised to the x -2. So this is going to go up 1 and right 3. So if I'm going to graph this, I know it's going to go up 1, so I'll put a dotted line in there. This line would represent y equals 1. And what that becomes is the new horizontal asymptote. Because it used to be the x-axis, and we take the whole x-axis and shift it up 1 unit. So this is our new horizontal asymptote. So where does it cross? Oh, but it also moves, which way? 3 to the right. So that would be over here someplace. And this line would have an equation, x equals 3. So it would be 3 to the right. So where do I plot my famous little 1 point? It used to be at 0, 1.
And 3, 4, 3, 2.
3, 2. It would get plotted from this intersection of these two lines up 1 unit. So this coordinate here is 3 to the right, and it's 1 above the line y equals 1, so it would be 3, 2. The rest of the graph is exactly the same as that one over there. From 3, 2 to the left, it comes down and approaches this dotted line because it is a horizontal asymptote. To the right of that dot, it grows exponentially. So you get a graph that looks like that. It's not that hard. The only confusion becomes when I teach you logarithms, the graph looks very similar, and you can get confused between which has a vertical asymptote and which one has a horizontal. That's the only big difference. How long do I keep you?
Come on. Seriously.
It's 1:30 to 2:30 to 3 o'clock, right? 3 o'clock. All right, what happens if I do this? Oops. 1/3 raised to the x. Now, you could do the table and find out where all these things are going, or you can use that neat little trick. As long as it has a 1 on the top, it's better to write it a different way. So what's the better way of writing this?
3 to the negative.
3 to the negative x. So if you go f of x is equal to 3 to the negative x, you could do it under a transformation. As long as the base is larger than 1, the graph is generally going to look like this, you know, hugging the horizontal asymptote, going through 1 above it, and shooting off to infinity. So 3 to the negative x is going to look a lot like that, but what does the negative on the x do to a graph? Which way?
Over the x-axis.
That would be a negative in front of the function. That would flip it over the x-axis. So a negative in front of the x is going to flip it over the y-axis, because all those x's that used to be positive are now going to become negative and vice versa. So if we're going to graph this thing, just a sketch of it, we would, well, this obviously becomes the horizontal asymptote. It's already there, so we don't have to draw it in again. You can if you want, dotted lines and whatnot. Color pencils come in really handy for graphing. So if it's flipping over the y-axis, instead of hugging it on the left and shooting off to infinity on the right, it's going to do the complete opposite. It's going to shoot off to infinity to the left and hug the asymptote on the right. So this graph is going to go this direction. 1 above, so this is the coordinate 0, 1. It's going to come down, hit this point, and then hug the x-axis on the positive side. Now, where this one describes money in a bank, you know, your money is going bigger and bigger as time goes on, this one describes something totally different. A lot of different ways of looking at it. It could be alcohol in your system. You went out partying one night and your alcohol content was this at the beginning of the night, and as time goes by, the alcohol in your system is flushed out. So drugs do the same thing. When they pump you full of drugs, they give you that little button if you've ever been on morphine, or if you've ever seen anybody with that button. They time it in such a way that when they push it once, the morphine shoots into your system, but over time the amount of morphine depletes. So they find someplace on this graph to keep it at a constant level where you can push the button again. Radioactive decay, you know, if you have a radioactive uranium-238, you don't want to be sitting next to it. It's going to be around for quite a while, but it has what's called a half-life. So after a period of time, half of it's left over. After another period of time, it gets cut in half again. So that has what's called radioactive decay because it's always getting sliced. Of course, it turns into something else. The rest of it, I think it's lead, uranium-238. All right. Now, graphing it is all well and fine, but it's not the most important part. Of course, the important part is knowing if it's decaying or growing. Those two are really important. But graphing it itself is not super important. Domain and range, remember domain and range? All that fun stuff? The domain here is all real numbers. The range is always 0, but not included off to infinity. That sometimes comes in handy. But more important is this concept. Let's go back to our little bit of money here. I'm going to change that to n. Let's fix the years at 15 years. So here, I haven't decided where to put my money, but I know I want it at 7%. I know I'm going to put $1,200 away, but I'm looking at different banks and they have different compounding factors. One of them might do it monthly, another one might do it daily, and so forth and so on. Who's missing a calculator? Both of you? Yeah,
Thank
you
you.
can share.
So nice of you.
Aren't I nice? So let's start off with n equals 12. What does a equal? And now since I don't have a calculator, I'm depending on you. I show you a nice, easy way to do this, but too bad. Make you do it the long way. So 1200 parentheses 1 plus 0.07 divided by 12 raised to the... Be careful with this 12 times 15. When you get to it, go caret parentheses 12 times 15. If you don't put it in parentheses, it'll spit out the wrong answer. So what'd you get? $3,418.73. Okay. So if I send it into a bank, do I have a confirmation on that? Does anybody confirm it?
Just give me 1 sec.
Give me 1 sec. Let's increase n from another bank. They're going to do it daily. Should it take the amount of money and greatly increase it if I compound my interest daily? That means they're going to pay me interest today. And that interest from today is going to get interest tomorrow. And that interest for the first 2 days is going to get interest on the third day and so forth and so on. Should it increase the amount of money I'm making? If I pay me interest more often than they were. It should. Will it increase it greatly? It might. I don't know. Let's find out. So if I plug in 365 into n, tell me what a is equal to.
I've got 3,428.83 cents.
It went up.
$10.
Went up $10.10. Woohoo! How exciting. Hey, it's money. Take it. Well, what if we could find a bank that would do it 10,000, well, let's start off with 1,000. 1,000 times a year, which would be about 3 times as much, as often. So instead of every day, every third of the day, about approximately. So what would A equal there? Do you think it'll go up more than $10? Okay? So you're expecting 34.38. What is it?
I got 3,429.05 cents.
And 5 cents. Ooh, it didn't go up that much. Now, this is one of those weird things in math. You would expect it to jump up because it's a larger number, but it barely went anywhere. It went, what, that's 17, 25, 22 cents? Lousy 22 cents. Let's find a bank that does 10,000 calculations a year. You would have to take 365 divided by, well, you would have to take a whole year divided into 10,000 equal pieces. I don't even know what that would be, like 10 seconds, 10 minutes, who knows. So this would be A is equal to, and I'll give you a guess, it's going to be 34.29
And 16 cents.
and 16 cents. So as n is getting larger and larger, this number is slowing down in its growth. That means, well, if you get to calculus, you'll see what it really means. But it pretty much means that the number is approaching a specific value. There's a maximum value. If you try n equals 100,000, I think, I'm quite sure, that number doesn't even change. Doesn't even touch it, doesn't even add on any more pennies. Now it might change some of the decimals afterwards, but as you raise that n, more decimals become fixed in place.
Might go like 5 cents.
It might even only go up 1 cent. It won't go up anything.
It went up 2 cents.
Seriously? Oh, I was hoping it would hold still. So that one would be a lousy 34.2918. Yeah. But eventually what will happen is it'll lock in a decimal place at a time as n gets bigger and bigger. So this has what's called a limiting value for A. Now if we're just talking money, I guarantee, I'm pretty confident that that's the limiting value for money. But if we're talking about all the decimals after it, there's a specific value that it's approaching. So we have to kind of look into what's going on. So one thing that we have to define is this. Take a guess what LIM represents? Limit. Limiting value, so limit. We're going to take n and we're going to shoot it off to this number, which is not a number. What's infinity? So it is walking in a circle. Infinity is this. Pick any number that you want. There's always one bigger. And once you get there, there's always another one bigger, and so forth and so on. So you never ever run out. So we're going to take this value and look at it. 1 plus 1 over n raised to the n power. And we're going to choose n larger and larger and larger. So let's start off rather large. We'll start off at 1,000. This one doesn't approach a specific number really quickly. So if you let n equal 1,000, what does this thing become? So parentheses 1 plus 1 over 1,000, parentheses caret 1,000.
I have 2.71.
2 point, keep going, 7, 1,
6, 9,
6, 9,
2, 3, 9, 3, 2.
2, 3, 9, 3, 2. I need more decimals, just so I can show you what's kind of cool about this. So that's n equals 1,000. N equals 10,000. I'll give you this. It's 2.71. I know that much is right.
8145927.
2.7. Okay. N equals 100,000. Now, I know this much about the number, 2.718. I know those numbers are guaranteed in this value.
Two, 6, 8, 2, 3, 7.
And up to this point, 2.7182. I think it's pretty much fixed to those values, I think. I can tell you in a second exactly what it is. So this is another one that it fixes the large part of the value and then it starts fixing all the small parts. So this one also has a limiting factor. Do you remember this number? What's pi equal to? 3.14.
So.
Yeah, and so. There's a lot more decimals after it. It's one of the more famous irrational numbers. This number 2, after you get it correct for a few more thousand decimal places, by the way, they have pi out to like 200 million places. Yeah, there's a group of people that want to find the next decimal place in pi, and they keep expanding how many decimal places they have. I don't know. Those are the weird math people. I'm not that weird. I'm not interested past maybe the 4th or 5th decimal. This one is also approaching a specific value, and kind of like pi, it has its own little unique symbol, and that symbol is E. So on your calculators, there is an ln on the left-hand side, so this. If you go second ln, it'll put E on your screen, and put 1 and hit enter. And it should be 7.1828,
1828.
and so forth and so on. It seems like it's repeating, but it's not. It's not. And it goes on forever. That number is E. It is this thing as n gets really, 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 really big. Millions,
So when you put
billions,
E in,
trillions.
is that formula? Or
When you
what?
type it in the calculator, you have to go second ln and then put a 1.
Right,
It's e to the first power.
okay.
E to the first power. But that's like 2.71828. So it's only accurate up to the 2. Too bad. But if you went up to 1 million, then the next place would probably stick in place. So this is literally the definition of what's called, oh, I went beyond my thing again. This thing is called, specially, the natural number. So it has a special name. It's called the natural number. And the reason it's called the natural number is it describes population growth perfectly. And it's used in a lot of sciences to come up with a lot of weird answers. And it's a very cool function. If you write e to the x, it's probably the easiest function in all of calculus, all of math, even though it looks a little funny. All right. At the end of the chapter, we'll come back to the compound interest formula, and we'll mix the idea of compound interest and the natural number, and blend it into one topic called population growth. Bacteria population, human population. Does anybody know what the population of the United States is today?
I bet you do.
I do.
Is it in the 3 billions?
Billions? I hope not, 'cause China only has 1 billion people. And India has 1 billion people. But we don't have that many. We have a lot, but we don't have that many. 320 million. Now, I teach another class where that number we have to use all the time, and I always try to find the accurate one. The beginning of this semester is 320 million. The beginning of last semester was 318 million. So over one semester, our population has increased by, do you know 2 million people? Guaranteed, most of you maybe, maximum, know about 150 people. 2 million is usually outside of people's can deal with. Has anybody ever been to New York City?
Mhm.
Have you walked around there? Are they all friendly?
Nope.
They ignore every human being on the sidewalk. You could be dying and they'd walk by you. Because their brains cannot comprehend more than the people that they already know. So they don't want to deal with anybody other than the people that they already know. They get that weird mentality. All right, how much time do I got?
9 minutes.
Sad. That's all right. The graph of e to the x, if you want to change it into a function just really quickly, it looks exactly like 2 to the x. It starts off small, hits 0, 1, and shoots off to infinity. So e to the x and 2 to the x are really very similar. Well, this one's really close to 2 or 3, depending on how you want to look at it. So the graph of it is no different than all the rest of them.